So, welcome back. In this lecture, we will discuss a compactness result. So, but before coming to that compactness result, let me make some comments again on the space H1 omega. So, this so what we proved in the previous class is the set of all C1 functions in the omega closure are dense in omega by using extension theorem and other results. Okay. So, one important subspace of this H1 omega. So, I just want to mention that. Okay. So, the subspace you take all C1 functions in omega with compact support, okay, and you take its closure in H1, closure in H1 omega. Okay. So, if we remove that compact support, then we know that this is H1 itself, but since we are putting that compact support here is denoted by H1 0 omega. So, in a minute I will explain what that 0 is, and in general this is a proper subspace. So, this is a closed subspace of H1 omega, but in general H1 0 omega is not equal to H1 omega. So, a simple example. So, in n equal to 1, if we take the interval, so we take H1 minus 1 1, and you take this constant function. Okay. So, this is in H1 minus 1 1, but it can never be approximated by a C1 function with compact support. Okay. So, this does not belong to H1 0 minus 1 1. Okay. So, a quick observation. So, since all these functions have 0 value on the boundary, so immediately we will get that. So, if u is in H1 0 omega, then is trace of u is 0. So, this is immediate, okay, because the any such u is approximated by a sequence of continuous C1 functions with compact support, and all those functions with compact support, they have 0 values on the boundary. So, this is immediate. So, what is important is converse is also true. So, namely, so we have this H1 0. So, omega is precisely set of all u in H1 omega such that trace is 0. So, to prove that if trace of u is 0, then u can be approximated by C1 functions with compact support. That proof is somewhat delicate, and it is again we have to do some delicate analysis near boundary. So, probably I will postpone a proof of that, but this is very important in the analysis of elliptic PDE, where we impose boundary conditions on the boundary of the given domain. Okay. So, this characterization of H1 0 omega as all those functions in H1 with trace 0 is important. So, one more thing I want to remark. So, again this can be shown, this H1 omega is a separable Hilbert space. So, I am not going to prove that. So, you can so its proof is on the similar lines like you prove L2 omega is separable, or more generally LP omega is separable for p less than infinity. Okay. So, that is the comment I want to make. And to prove the compactness result, we borrow a result from functional analysis. So, let me just state that theorem. Okay. So, this we are going to use to prove our compactness result in H1 omega. So, let H be a separable Hilbert space and M a subset of H. Okay. Suppose M epsilon is again a subset of H. So, this parameter H is positive, such that for each M, each F in M, there is, let me call it G, okay, G in M epsilon, such that F minus G is less than or equal to epsilon. So, you can even put a constant as long as that constant is does not depend on F or G. Okay. So, if so, this is the conclusion. So, this hypothesis, if there exists a sequence epsilon k tending to 0 from positive side, no, if for okay. Such that all you take this M epsilon k are relatively compact or pre-compact. Okay. So, since we have not added we are not assuming that these are closed. So, we can only say that relatively compact. So, if we can find a sequence of this epsilon k approaching 0 such that all M epsilon k are relatively compact in H, then M itself is relatively compact. So, some books they write instead of relatively compact they write pre-compact. Okay. So, this we are going to now use to prove our once we assume this is not difficult. Okay, so here is the theorem. So, compactness so again what I mean is relatively compact. Once we take the closure, that will be compact. So, every bounded set M in H1 omega is okay. So, again let me just stress that relatively compact. Obviously not in H1 omega, because this is a Hilbert space. Every bounded set at the most it can be weakly compact, but compact in L2 omega. So, this is important. Okay. So, in other words, if you have a bounded sequence in H1 omega, we can claim that there is a subsequence which converges in L2 omega. Okay. So, this is the statement of this theorem in other words. Okay. So, proof. Okay. So, we have since M is bounded, so F H1 omega is less than or equal to some constant for all F in M. Okay. So, this is given to us, okay, and want to prove that this set is relatively compact in L2 omega. Okay. So, that is so first assume okay. So, this the trick all the time we are using, if you notice several proofs. So, M is in H1 0 omega. So, that means we are assuming all the functions in M have 0 trace. Okay. Okay. So, now let us do some computation. So, we have already done that. Okay. So, again recall the modifiers, Okay. So, this F epsilon, F star rho epsilon. So, F is in M. Okay. So, since we have done this computation many times, so I will just write that. So, we have F epsilon minus F in L2 omega less than or equal to some constant, let me write as, so epsilon is positive. Okay. So, that is by epsilon to the n is the dimension. So, this integral over this mod z less than epsilon dz. So, just write the definition of this convolution and this L2 norm, you get that. Okay. So, this, and again I am using the property that integral of rho epsilon is 1. Okay. So, this is omega f of x plus z minus f x square dx. Okay. So, we have done similar estimates earlier. So, you just recall them. Okay. So, now what we do this, so we write this f of x plus z. So, the inner integral. So, we just write this. This is from one variable calculus. So, this is just 0 to 1 d by dt of f of x plus tz dt. Okay. But this one in absolute value we can estimate this grad f of x plus tz just by chain rule. Okay. And then you get mod z square, because I am differentiating with respect to t. Okay, let me just write that, because we are taking anyhow square there. So, let me just write that. Okay. Now, you put so that is simply just okay, let me write that. Okay, f of x plus z, taking the square, less than or equal to grad f x plus tz square so 0 to 1. Okay, so this dt into mod z square, and that is less than or equal to mod z square this f in h1 omega square. So, this involves only derivatives. So, I am also adding that L2 norm. Okay. So, now using 1, sorry, so I have to okay. So, this is integral over omega dx. So, this is over omega, and then you interchange the by Fubini, you get that. Okay. So, using 1, so we get this f epsilon minus f. Actually, this is first you prove this using assuming okay, not that one. So, this you first prove. So, first assume f is in C1 C omega and extend by density. So, you see how approximation by smooth functions help us in obtaining many estimates. Okay. So, this L2 omega is less than or equal to some constant square f in h1 omega. There is still a dz integral sitting there. So, you have just z integral is mod z less than epsilon. So, we can just this mod z square we can replace by epsilon square, and there is an epsilon n here, and then you get mod z less than epsilon dz, and this gives a power of epsilon. So, the whole thing we get. So, C 0 another constant, okay. So, I am not bothered about that. So, where C 0 tilde is independent of f and f in M, and this comes from the assumption that M is a bounded set. Okay. So, we are using that. Okay. So, this finally, this estimate does not involve this constant depend on constant will not depend on any f. Okay. So, we have this, let me call it 2. Okay. So, each f in M we are approximating by a smooth function f epsilon, remember it is a smooth function. Okay. So, now consider this set epsilon, because we want to M epsilon, this is set of all f epsilon, f is in M. Okay. So, we are going to apply that abstract theorem from Hilbert space. So, now it is sufficient to show epsilon is positive. Okay. So, now it is sufficient to show that the each of M epsilon is relatively compact in L2 omega. Okay. And then we can apply just that theorem, and then we have the compactness result. Okay. So, what so claim, this is the claim. So, remember these f epsilons are continuous functions. Okay. So, claim M epsilon is relatively compact in C omega closure. Okay. Once we show that, this will imply that M epsilon is also relatively compact in L2 omega. That is just one step. And to prove the claim, we just apply Ascoli-Arjala. Okay. So, to prove the claim, we apply Ascoli-Arjala. So, for that what we have to show? We have to show that this M epsilon, okay. So, we need to show M epsilon is equibounded and equicontinuous. Okay. So, just remember epsilon greater than 0 is fixed for the argument sake. Okay. So, if so this is again very clear. So, first we get the equiboundedness and then we get the equicontinuous. Okay. So, now we have f epsilon x. So, we can be very crude here. Okay. So, because epsilon is positive, so we can just carry it. Okay. So, this is just use the definition of f epsilon. So, since omega is bounded, this L1 norm can be estimated in terms of L2 norm, and again since f is in M. So, I just write this as some independent of f. It may depend on epsilon, but that is okay. Okay, that proves equiboundedness. So, this is true for all x in omega. So, this constant is independent of f as well as that x equiboundedness. So, to get the equicontinuity, we estimate the derivative. Okay. So, next, so similar argument. So, next del f epsilon by del x I. Okay. So, same again estimate. Now, in fact, we get another. So, the constants are different at every stage. So, this is coming from the derivative of rho epsilon. Okay. So, again you have the same thing f y dy, and since again this is omega is bounded, this L1 norm is estimated in terms of L1 norm and that in L2 norm and then that in terms of the H1 norm. So, again we get, so maybe double. Okay. Okay. So, that proves the equicontinuity. And so, the set m epsilon for every positive epsilon is relatively compact in C omega closure, and that implies it is also relatively compact in L2 omega. Okay. So, for the general case, so if f is in, so that proves the theorem. Proves the theorem under the assumption. Okay. So, this important assumption. So, we are assuming that. So, then only we could estimate that f epsilon and with f. So, if now you consider this one H1 omega. So, use extension regions. So, what you do is, so just I will call it M extension. Okay. So, this is set of all f in H1 0 omega tilde. F is an extension of some f in M to H1 omega tilde. Okay. So, this we have done earlier. So, now you apply the first part to this f extension. So, since all these, so we have this is important H1 0 omega tilde is constant, whatever this extension is. Okay. And since these are all bounded for f in M, so we get this M extension is also a bounded set in a larger domain. So, that is relatively compact in L2 omega tilde. So, since omega tilde is large, so omega tilde anything that contains. So, we get relative compactness in L2 omega. Okay. So, fill in the last few lines. So, this completes the proof. So, there is a similar result of relative compactness. So, if you take again any bounded set in H 1 omega, now you collect the traces of all those functions in that bounded set, and that set of traces is relatively compact in L 2 of del omega. In general, you can take any smooth surface. Okay. So, I will stop here, and now we will see an application of this compactness result to some equivalent norms. Thank you.